would be good not to forget to ask to Fritz to explain to us the analysis he made of the negative prices, and that he had to skip.
This is yours?
Yes, but it's the PowerPoint.
The short one.
Yes. Oh, yeah. Cool.
No.
It's the cool.
Okay, so I'm not really a man of scenarios. What I'm really doing is really more looking at data and essentially mostly in relation to the French electric system, I understand. But I nevertheless found this very interesting poem by a 19th century English poet, and I think it was so beautiful that you had to have a look at it. The rest of the poem is good too, but it doesn't deal with wind anymore. And so we are certainly for scenarios what people think is important, and some of our colleagues yesterday, German colleagues, said that in Germany the people had a very specific vision of concerning energy, and then so it's interesting to look at what French people think. And this is a diagram that shows what this type of diagrams, qualities, 8 qualities, and then the largest the surface, the best it is. And so you see that corresponds to France, and so you see Europe does exist, because in France we also think that solar is the ideal energy, wind is the second best. The interesting thing about this diagram is that the intermittent renewable electricity is better considered than that which is not. That's frank. And of course, nuclear is bad in every aspect. Even in terms of performance, you notice that solar is almost as good as nuclear. Okay, and another thing which I learned recently is the question: do you think that within 10 years will be possible to produce almost all the electricity that France needs solely by means of renewable? And then if you do an analysis, then you realize that 1/3 of the French thought yes, that by 2021 there would be a situation. But the women were more optimistic than the men on this subject. And now if you look by age, then you realize that the young people are really optimistic, and while the old guys really. And so you get to the conclusion which says that in France, the most fervent supporter of electric renewable is a young, because there is also an analysis by political inclinations, but so a young woman voting left is really, and I have the feeling that from talks I heard, I'm feeling it's not only true in France. And then the less opposed to nuclear energy is an old man voting right. That's okay. So maybe I should skip this, because that's well, maybe here it's a description of where the how the French policy is concerning wind is organized. So here you have all the regions of France, each and the green squares corresponds to this scale here, which is the efficiency or the load factor of a given turbine in any of these regions. So you could see that my region, Languedoc-Roussillon, is really at 31. And of course, the average French for the last year was 23%. And but on the same curve, I've plotted where are the wind turbines in France. And the interesting thing is that you find that basically we never put wind turbines when there is wind. Because basically what you find, the 6 most equipped with wind turbines regions, only one has a load factor which is above the national average. So that shows that in the land of Descartes, wind is not always the motivation for setting up a wind turbine. Okay, so now I'm going now to analyze 2 scenarios which have a sort of official standing. The first one came with the Grenelle de l'Environnement, which essentially said that by 2020 we would have 25 gigawatts of installed wind, 19 onshore, 6 offshore. I must say that it's very doubtful that we'll reach this. I mean, if the present numbers go on, it's doubtful we'll reach that, but that's not the point. The essentially point is that in all French official documents, important CO2 emission reduction is put forward as the main goal to be attained. And generally it's followed by things like energy independence, cost, green job, increased proportion of renewable in the final energy mix. Note that it's not in the electric energy mix, but the commitment of France is for the final energy mix, which in principle includes also thermal renewable. And so the French emissions are indeed important because they are about 350 megaton in 2011, and so that means basically 1% of the world emissions. But the electricity production sector only accounts for 8%. So that led, for example, the accounting court, the Cour des Comptes, to ask, why should public spending be devoted to electric renewable? If this is the goal, why should be devoted to electric renewable rather than thermal renewable? But the point also is that the court expressed doubts about the fact that this electric renewable would do much on the three following subjects: independence, job creation, and low cost energy. The point also is that, in fact, if you look at the situation in 2013, if you compare the hydro, wind plus solar, the total production was 96.2 terawatt hour. And now if you look at Germany on these three subjects, so of course there's the biomass electricity too, but these three subjects, you see it's not so bad, the situation in France. Okay, but the point was really to test the Grenelle wind plan. And so the idea was we use data, again, real data, acquired over these 2 years. And then we started from a situation where the wind fleet was 5 gigawatts. And then we imagined that there would be 20 France countries living under the same climate, temperature and wind, the same electric consumption, with a wind fleet that would be 1 gigawatt more, 2, 3, up to 20, so that we would reach 25. And then the question is, we made the following hypothesis: the wind production grows in proportion to the power, priority for ejection of wind, and of course priority is given to reducing CO2 emission. And of course, among the renewable energies, solar can be used, only hydro can be used for balancing. And since France is exporting almost all the time, you can't count on this to participate to adjustment. And so the first consequences is that it's only the dispatchable productions that can contribute to generate the balance. And of course, since we really want to stop CO2 emission or reduce CO2 emissions, then we use it to stop coal-fired, gas-fired, and then oil-fired power plants. And I made all sort of hypotheses that were all systematically favorable to CO2 emission because I wanted to get an upper bound. And so the grid accepts everything. The two grid managers coordinate perfectly. There is no energy loss associated transport. The thermal plants adjust instantaneously. All hydro can be kept in storage, whichever amount is required. And when hydro is used, there is always a turbine which is available. And finally, pumping stations are put to the exclusive service of helping wind. And so the calculation is done 3-step. The first step is that any available new wind power is used to stop coal, gas, which was produced at the same time. Then hydraulic is that when after step 1 there still remains some unused wind power, one stops immediately any flow of water from the reservoirs, and this saved through wind water is used later to stop any coal, gas, and oil power which is not saved at step 1. And then the step 3 is the pumping station come in. And then our pumping station are right now 5 gigawatts, 100 gigawatt capacity, so essentially 50 50 times below the figure that you have been using for storage. That's our situation now. And I think it's probably slightly better than Germany. And then we do the same thing. We use the water to save, to stop power. And of course, if there still remains some unused wind power, you stop nuclear power plants. And of course, you don't gain anything from that. So here I took a month of November, and here you have the wind load factor. That was an interesting month because the first part of the month was warm and windy, and the second part was cold and without wind, essentially, or with little wind. So in a sense, it represents a situation typical of winter in France. And so below, I show you what happens when you have 25 gigawatt of total wind, and then you can use this wind here to stop. For example, here you only stop the coal plants. Here you have stopped the coal plant and you start stopping a gas plant. And then, here you have stopped both the coal, the gas, and then there's still some remaining wind. So you use it to keep water in the reservoirs and so on. And of course, when everything has been done, you stop nuclear power, which corresponds to the red zones. And so that's the step one. The step two, you are using the hydraulic water which is being stored here to stop some more coal or gas plants, or even here some oil turbines, in fact, which are rarely used. And finally, here, when you have the green zone, the pumping stations are being used, but of course, after some time, the pumping station is full, so it means we have to stop nuclear, but we can use this remaining energy to stop some more of gas power, of coal power and gas power, but at that point, there's nothing left in the water, so you cannot do anything more. So that's the general scenario which is pursued over a year. And so now what you can do is you look at the maximal reduction, and so on the abscissa you have the additional wind power from 1 to 20, and on the ordinate the kiloton of CO2 which is avoided in the 3 different steps. And essentially what you do find is a law of diminishing returns. The first gigawatt can help you save something like 1.6 megaton, but the last one would be more around 400 kiloton. And so basically the integrated gain, that means when you integrate over the curve, what you do find that in the best case you'd be ranging between 16 to 20 megaton. So basically from the scenario, the CO2 emission can't exceed 4 or 5%, and of course we have to remember that our goal is 75%. And now you can ask the question, how many power plants can I stop? And then you realize that the first gigawatt helps you to sort of discard or pull out something like 100 megawatt of coal-fired power, but the 20th additional gigawatt allows you to pull only 120 megawatt of coal and gas-fired power. So we started in France with a total of 12 gigawatts, and we have sort of saved, we can sort of pull out about 2 gigawatts, and we still have to keep 10. Because there are moments when it's needed, despite the fact that we have deployed about 25 gigawatt of wind. And so now it's an analysis of the ADEME scenario, which was presented this morning, but only the electric part. So the ADEME, as was said, is this agency, and of course it depends on the Ministry of the Ecology and Energy and Development. And so ADEME are thus much in line with government views. Okay, so I like the scenario because it is of great interest, because everything is said. You have the power, but you also know the energy production, so you can really work on it. It's not the case with many other scenarios. And I only analyzed the 2030 part of it because of the conclusion I reached the point is that it's a very voluntarist, 21% reduction, so which amounts to minus 25 per capita. The consumption, I mean, the scenario says already that we are overproducing electricity. 83% of the consumption is 83% of the production. There is, of course, the strong reduction of nuclear energy promised by our president. And then the power drops to 32, and the production is now mostly base load with a load factor which is close to 7,000 hours. And of course, there is a strong growth of intermittent, and we are told that they are 20 times more efficient than in Germany of that time, and wind is assumed also to be 3% more efficient than France of 2012. So all this is going to be taken into account. So nuclear plus solar plus wind, 95% of consumption. And hydraulics comes in and so on. So essentially the calculation was made using data, observed French, observed German, and scaled to the power and to the additional efficiency said into the scenario, and nuclear was turned to base load, 17% in summer, 32% in winter. And here is the curve. So here you have the reduced consumption curve. So it's reduced by minus 21% over this period, and you can see the weekly oscillations and the daily oscillation of the consumption. And of course, on the top of that, there is this famous event that took place in February 2012, where essentially we reached 102 gigawatt of power, which of course now is reduced to 77 gigawatts. So that's the consumption. And here what I've drawn is the curves that remain to be managed, either produced or exported, when you take the consumption and you suppress the nuclear, the wind, the solar, which corresponds to an installed power of 111. And then what you do find is this curve. So you could see from the fairly predictable oscillations of the human activity, then you end up with this curve that you have to manage. And the point is that you are still missing at one moment 36.2 gigawatt, which implies that you will have to import because there is not enough in the scenario to cover that. But the interesting thing is that on this side, you already have a maximum overshoot of minus 31 gigawatt. And that's interesting because the only thing you can do with it is to export it if you want to keep it. And we only have 13 gigawatt of export HV line. And generally, it takes more than 10 years to build 1 gigawatt of HV line, as the experience with Spain has shown. And finally, globally, that's my last transparency. Over a year, the scenario consumes 369. And with 100 gigawatt of nuclear wind, it already produced 354. But when you do the calculation, 45 terawatt hour are still missing, and 29 terawatt hour have to be exported. And the interesting thing is when you look at this picture, it looks like it's random, but it is not. It has the same structure that Fritz Wagner showed, namely, when you look at it, that's what happens. If you look at the early structure of this difference, what you do find is that, in fact, there's always a night deficit that you have to compensate with production or import. But the interesting thing is that you have a day excess. Excess production must be exported. And so, essentially, that means in this scenario, France must export at the same time that our neighbors are doing the same. And to show that, it was mentioned that Germany was exporting through the Czech Republic, but that's not only the case. Here you have something that I took from the grid operator report, which came out 2 weeks ago. And here you have the German wind and solar. So this is the wind, and this is the wind plus solar German with this scale. And here you have the situation of the traffic balance between France and Germany. And you can see that each time there is sun in Germany, we are importing. No, doesn't mean that we are always buying it, because at the same time, we can see that there is a flux to Switzerland or to Italy. So it could be that the electrons are just passing through France. But certainly, we are, there is an export which also takes the French route and not only the Czech route. And so now, and that's my last, I want to say that in my slide you'll find information on the solar and wind production for the year. Here it's an analysis of the coherence, which in fact is rather weak between wind and solar production and consumption. Here is something that was mentioned yesterday, where I provide an analysis of what would happen if there was a European copper plate for the wind, where basically everybody would sort of put into one pool the wind production. And here is also an analysis of something that might be relevant, is what's the quality of the day-ahead predictions of wind and solar in different countries. And I've added something which I think is interesting, because concerning what nuclear plants can do in terms of balancing, I think I've heard things which doesn't seem to correspond to what the data shows, so I've put in some. And so this is really the end. So here it's a wonderful machine, because it's completely ecological. It's a solar wind turbine. It also has a quality, it's a present from my granddaughter, which so reminds me why I should be interested in energy. And note also that if you look at the picture, it's also anti-nuclear, so it's absolutely perfect. And now, the other thing is, another thing I would like to mention is, could this influence the future energy scenario? So if you look at the Duden dictionary, which is sort of the reference dictionary in Germany, like the Robert in France for the living language, or the Collins in UK, you find this new word, die Verspargelung. And die Verspargelung is a construction typical of German language, which starts from the root Spargel. And Spargel means asparagus. And so that means essentially, the way you would translate that would be asparagusization. It's difficult to pronounce. And it essentially means transformation of a landscape to look like a field of asparagus when you have planted enough wind turbines. So note that the word Vermeisung, which corresponds to using land for biogas, is also part of the German language too. And so, thank you.